Yeah, so welcome student to today's lecture. So let me start lecture. So MA415 Algebra, okay, and then this lecture number 21. Okay, so now so recall that so we define about integral domains and their properties, right? So today we will learn some more little bit some definitions about rings. So let me start with this. So suppose obviously we learn about what is a subring also. So let me discuss little bit. So definition. Suppose we have two rings, say R1 and R2. Okay. And when I am saying rings, I mean with respect to two operation plus and dot. Okay. So we define something called ring homomorphism. So this phi is said to be a ring. Some problems. Sorry. Ring homomorphism. I don't know. There is some problem. Is becoming very slow. Laptop. Ring homomorphism. Oh my god. Laptop become. If okay, so I think there is some problem. Laptop become very slow. Okay, so if what happens? So um, this phi of a plus b equal to phi a plus phi b. Okay, and this is true for all a b belongs to this R1. So what does that mean? That means this first property. So that is phi is a group homomorphism. Group homomorphism under addition, the first operation, right? This first property. And what is second property? Second property is that phi of a into b equal to phi a into phi b is also true for all a b belongs to R1. Okay, so if and obviously you can also say that 0 goes to 0. You can write that you can find out from this property 1. Okay, so if you have phi we satisfy these two properties, then it is called a ring homomorphism. Okay, and then the moment you define homomorphism, then with that you define something called the cardinal homomorphism. And what is this? So this is by definition the fibers of 0. Okay, so what does that mean? That means all those, say R belongs to R1 such that phi of R equal to 0. So this is 0 in R2. Okay, 0 in R2. Okay. Okay, so that is this is um, 5 hours of 0 under 5. Okay, so this is called the kernel of the homomorphism or ring homomorphism. Okay, and similarly, if you have a bijective morphism, then it is an isomorphism. So what does that definition? So an isomorphism of rings is a bijective ring homomorphism. Okay, then equally it's a isomorphism. Okay, so maybe you can give some examples. So there are plenty of nice examples. So one of the most important. Oh my God, what happened to this? Huh. So examples. So I already we learned that these rings Z and Z mod say and Z. Okay, these both are the rings we already know. Okay, and we can obviously define this map. What is the general map? So you just okay. So what's the general map? So if you take any integers, okay, and then if you quotient modulo take quotient modulo n, then what will be happen? Then this will be image of this, right? So you write down any n and send it to n. Sorry, I should just say n here. So some a, and you write down a mod n. Okay. So your map phi send a to a bar. A bar is Ever is this what is ever? Ever is kind of congruent to a mod n, right? Okay, so this will be the simple ring homomorphism. You can easily check that phi of a plus b will be equal to a plus b whole bar, which is nothing but a bar plus b bar. Okay, and this is obvious, right? Is the property of congruence modulo n. You can check, and also you can check that phi of ab equal to ab whole bar, which is nothing but a bar into b bar. Okay, so this is a general simple homomorphism. We can easily do it, and also you can multiply. See, obviously identity is always an isomorphism of any ring, and you can have some other maps. For example, suppose we have a field and you are just taking okay, so you start any field f and then you have some say quotient, sorry, polynomial ring. Okay, then you can also always define the natural homomorphism from fx to x. So this is the polynomial ring over the field f. Okay, and what would be the natural map? So you can define phi of fx to what? To f of 0. So f of 0 is what? F of 0 is the constant term. So this is the constant term of fx. Okay, the polynomial. Now you check that this is a natural homomorphism. Okay, so you can easily check ring homomorphism. Okay, and you can also find out what is the kernel. Okay, so find out what is this kernel of phi? Homework. This is not very difficult, simple problem. Okay, so um, so you can also always define such homework with a very natural, right? So obviously you can ask these properties, maybe some properties. What about kernel? So let me just first take that R1 from R2 ring homomorphism okay. Then this kernel of I is a actually subring of R1. Okay. Now you can easily prove this subring of R1 and then prove is like that. So what you need to prove something is a subring of that. That you need to prove that if so, let say A B belongs to the kernel, and then you need to prove what? You need to prove A minus B belongs to the kernel and A into B also belongs to the kernel. So what does that mean? So if to prove A minus B belongs, so A B belongs to kernel means what? That means that phi of A equal to 0, which is also equal to phi of B. Phi of B is also equal to 0, right? So I need to prove that what is phi of A minus B. So what is phi of A minus B? So by property, phi of A minus B is nothing but phi of A minus phi of B. Okay. Okay. So phi of I must say one more line. Phi of minus B, but phi of minus B equal to minus phi of B. Okay, you check it. This is simple property, and then this is nothing but 0, right? So what does that mean? That means A minus B is also inside the kernel. So A minus B is also inside the kernel of phi. Okay, and similarly for phi of A into B, you have the property that is phi of A into phi of B, right? So what does that mean? So phi of A into phi of B, and it is also 0 because phi of both is 0, so it's 0. So AB belongs to kernel of phi. Okay, so what does that mean? So you just know that phi kernel of homomorphism is a subring of R1. Okay, and like homomorphism for groups, here also you have image, so you can write down image of phi is a, remember that was a subgroup for group, here also it is subring of R2. Okay, so again the proof is simple. So how to prove it? So what you need to prove? You need to prove that let you have two elements, say A and B belongs to the image of phi, then A minus B and A into B belongs to image of phi. Now if A and B belongs to image of phi, then what does that mean? Then there exists some x and y belongs to R1 such that what happen? A will be something like phi of x and B will be something phi of y, right? For some x and y, and hence A minus B will be equal to phi x minus phi of y, which is nothing but phi of x minus y. So what does that mean? That means A minus B is the image of x minus y, right? And hence A minus B belongs to image of phi. Okay, so this is obvious. And similarly, for product also, for product case, you see that so what I see, okay, A and B are x, right? So your A into B, you can write down nothing but phi of x into phi of y, but this is homomorphism, so by the property it is phi of xy, and hence AB is also element of image of phi. Okay, and hence image of phi is a subring of this R2. Clear? So these are the property of homomorphisms. That tells you that both kernel and the image become the subring. But you see, the kernel has one more property. So not only it is subring, it has one nice property. So what is the nice property? So you can see here, if you take any element from the kernel, say A, suppose A belongs to the kernel of phi, and you choose any arbitrary element R1, then you see that A into R or whatever, like you choose A, R or RA, doesn't matter. They are actually element of um, this kernel, right? Kernel of phi. And that is obvious because if phi of AR you can write down as phi of A times phi of R, and phi of A is 0, so it is 0. Similarly, phi of RA equal to phi of R times phi of A, and again phi of equal to 0. So both so A into R, IR, both are actually element of the kernel, right? So this is a very nice property, and this property we would like to now discuss. So now recall that we define something called cosets, right? What was the definition of cosets? So on a group, when you subgroup, then you define the coset of that subgroup by what? You define a equivalent relation on the group G with respect to each and equivalent classes, right? So similarly we can also do here. So now let me play the same game here. So let R be a ring, and your subring, so S be a subring of R. Okay, so we define we define uh, we define a relation on R by how we define that that R1 related to R2 if this R1 minus R2 is the element of S. Okay, so this is my definition. So I am taking that if two elements are related if their difference is element of S. Okay, so now you can check that this is now check that this tilde is an equivalence relation. Okay, so reflexive obviously, and symmetric and transitive. Okay, so symmetric because whenever something is there in say subring, the negative element is there, and transitive also property of subring. Okay, so this is equivalent relation. So the moment you have equivalent relation, what you know, equivalent relation forms a partition, right? And so these are nothing but equivalent classes. Equivalent classes makes a partition on the set R, right? So now we define this. So we define the symbol is R is nothing but this equivalent class of this is this is uh, this is what this is all those some r dash belongs to r such that r related to r dash. Okay, so what does that mean? That means r minus address element of s, right? So this is kind of equivalence class of R. Okay, and this class we called, okay, so sorry, R plus S. Sorry, this is I write down by say R plus S. Okay, so let me write down by R plus S. So yeah, so equivalent class of R such that R minus, yes. So you collect all those elements R dash such that which are related to R. So that means R minus R dash element of S. So R dash you can write down as R plus S. Okay, R dash minus R. Okay, or you can say R dash instead of this. You can say this R dash related to R. This is the same actually. No problem. But conventionally you can write down R dash related to R. Okay. So now this now we define this. There is something called, okay. This structure R divided by S. So this is defining that this collection of all kind of element of the form this R belongs to R. So this is what this is, collection of distinct this, I mean this is kind of left corsets, right? So you can define by right, but see in addition, it's addition with respect to addition, the ring R is abelian, right? It is commutative, so it doesn't matter. So this collection of cosets of S. Okay, so the natural question whether inside this collection we can define the ring structure or not. Okay, whatever we have done for group theory, can we play the same game here or not? For example, we have a natural, obviously it's a natural map, right? So R cross S to R cross S by S, the addition is a natural map, right? This you take R1 S and then R2 plus S, so that map to R1 plus R2 of S, right? So what is that? That is R1 is plus R2. This is addition map. So addition R2S you can map to. You can write down this as R1 plus R2 of S, right? So the way we define this looks very much natural. Now can I define the multiplication also like that? So let us try to define. So if we define multiplication from this R mod X to R mod S by R mod S, like this, say R1 plus S into R2 plus S, and suppose this is mapped to this is mapped to R1 R2 plus S. So can I claim that this multiplication is well defined? So what does that mean? So I'm saying that this with respect to multiplication, can I say that they form a ring or not? Okay, so you remember in group also, if you have a group, a subgroup, and you take the left cosets of the subgroup and you define on the subgroups that the two maps, right? Addition, multiplication, and then you talk about those maps are this only if and not, right? And to do that, you check that it is only if only the subgroup has nice property. It's called normality, right? If the subgroup is an all subgroup, then only that exists, right? So same thing you can play here, and you check that this is true if something happened. So it's what something happened, then so so this R mod S with respect to this, the way we define this from say ring, okay. If I not leave, what happens if I not leave the S has some property. What is that property? It has the following properties. So what are the properties? So you see, you multiply from here, you just try to check. So this is true for every, this has to be true for every R1 plus R2 belongs to R, right? Now so yeah, so what does that mean? So let me find out. So suppose instead of R1, so R1 inside this class of R1, right? This R1 plus S, and you choose R2 inside R2 plus S, the equivalent class of this, right? But instead of choosing R1, if you choose another element, so say for example R1 plus something X, that also inside the same thing, and instead of R2, if you choose anything another thing, R2 plus something, R2 plus S, then can these two things are equal? So R1 plus S into R2 plus S should be equal to this, should be, because they're the representative. So if this map is well defined, that means that it should not depend on the it should not depend on the representative, right? So this plus S so into R2 plus Y plus S, right? So what does that mean? So that means on the one hand R1 R2 plus S should be equal to this. So what is this? This is yeah, so the way we define, so A plus this plus this equal to R1 plus X into R2 plus Y plus X, right? This is the definition we define here. Where is that? Yes, this equal to this into this plus X. So these two things should be equal, and then only you can say that this multiplication is well defined, and then you can obviously the rest are simple, right? So this is the important thing you need to check. Now you see that this has to be true for all R1, R2, X, Y, that all element of that R, right? Now in particular, when R1, R2 equal to 0, then what happens? When R1, R2 equal to 0 both, then what you will have? You have that X into Y plus S has to be equal to S. So what does that mean? That means X, Y has to element of S, right? This is quotient, right? So H, A plus H equal to H means A belongs to H, and this has to be equal to for all X, Y units to R. So what does that mean? That means A must be closed under multiplication. A is already closed under addition, you know, right? Suffering. Also this is also coming from that. And not only that, if R1 equal to 0, then what happens? If R1 equal to 0, okay, so let me say, so if R1 equal to 0, then what happens? Then R2 and R2 is arbitrary. Then what happens? Then from this equation you can easily say that this X into this, so X R2 plus XY is element of S, right? And you already know XY element of S, so X R2 element of S for all X belongs to R, and R2 belongs to R. So what does that mean? So that means that the property of kernel I showed you, right? Okay, so no, 1 minute. This is not only x1 belongs to this, xy also element of S. Yeah, so this property I need to check. Yeah. R1, yeah, so R1 plus X is element of R1 plus S. So X belongs to S, Y belongs to S. So this is the property. Yeah. XY belongs to X. Okay. So X belongs to S. Okay, and so what does that mean? So we just showed that the kernel has the same property. If you choose an element from kernel, choose another element from outside the kernel and the whole any ring, then the product is element to the kernel, right? And also for if say R2 equal to 0 and R1 is arbitrary, okay, then you see that okay, so from this equation let me see, so R2 equal to 0, so this is for the 0, and then R1 into Y, and this implies R1 into Y is element of S for all Y belongs to S and R1 belongs to R, right? And also this property also, so it's kind of absorbing element. If you take product element of R from right side is absorbing, also from left side is absorbing, right? So it's absorbing from both sides. So clear. So so this is the nice property is to have. Then only this map become well-defined map. Okay. So what does that mean? So that means okay. So now let me write down this property as a name. So we define um, so definition. Let R be a ring, and so let me write down this is a nice symbol I be a subset of R. Okay, and then you defined for any element for any R belongs to R. What do you define? You define this R of I is kind of um, so this is kind of a multiplication of element of I into this I, such that I is element of capital I, and similarly you can define I into R by the other way, I times R, I belongs to capital I. Okay, both ways. So this this is my sets, and then what do you do? We show that this so that we say I is a left ideal of R if what happened if two things happen. If first of all you I is a suffering, okay, and second thing this R times I, the subset of I for all R belongs to R. Okay, so what does that mean? That is closed under multiplication by left side. Okay, so then it's called a left ideal. Okay, similarly you can define right ideal also. Right ideal, for right ideal, what do you do is you would say that R is a subring, and then I times R, this is subset of I, sorry, yes, this is from right side. for all r belongs to r. Okay, this is for right ideals. Okay, ideal. Okay, so then finally, what do you say? Say finally, um, a subset I of R is called an ideal, or some people also call it a two-sided ideal. Okay, two-sided ideal. An ideal of R if I is both a left ideal, both a left and a right ideal of R. Okay, so what is the ideal? Ideal means this is from left side and right side, both sides. This is this can be absorbed, right? And in that case, so if you have an ideal R, then you can obviously define those maps. You can define this R mod I. So this is what? So this is your R plus I. R belongs to R, and this forms a ring under the above two operations. Okay, and these rings, and so this ring is called the quotient ring. Quotient ring of R by I. Okay, so you understood what is a quotient ring? Quotient ring. Yeah, okay. Okay. And so this is a simple observation. Now you can also maybe I will give you some first some of the examples, and then uh, obviously, yeah. So one thing I need to also tell. So I said that if that forms a well-defined property, then they must be ideal, right? But what about the converse? Converse means if it is an ideal, then that maps are well defined or not, you check it. It's simple, not a difficult property. You can easily check it. Ideal property tells you that um, map is also well defined, right? So that you can check. So now let me give some of the examples. The natural example. So you have Z plus dot. So this is your ring R. Okay, and then you see that you define this in Z. Um, so in Z is what? So this by definition kind of n into A belongs to Z. So this is kind of multiplicative. This kind of all those elements of Z, which is a multiple of n, right? So this is an ideal of Z. Now how to prove this ideal of Z? So first of all, you have to check this is subring, and this is obvious. So to prove how, so obviously 0 is an element of NZ, right? So this is obvious. So this is not equal to 5. So this set is non-empty set, not equal to 5. And so if you choose two elements from here, so one is in A1 and in A2 belongs to say NZ, and then you say that in A1 minus N, A2 is nothing but N times A1 A2, and hence is element of NZ, right? So this is closed under that negative things, negative elements, and similarly n into A1 into n into A2 is nothing but n times whatever. This is also element of NZ, right? So NZ is a subring of Z. Okay. And second property, you need to check that this kind of absorb, right? This property. So one thing is clear from here, that the ideal is actually this analog of, okay, yeah, so this is kind of analog of normal subgroups, right? Normal subgroups. Okay. So you need to check whether it's absorbed or not. So you can easily find out that. So how to find out is absorbing those is absorbing or not. So what you do, so you take select some NA belongs to say Z, and something say R belongs to Z, and obviously you see the R times NA is nothing but in RA, that also element of NZ, and also NA times R, it's also in, yeah, whatever, so it's also element of Z, right? So in any case, NZ is both sided ideal. Okay, so this tells you that NZ is an ideal of Z, right? Both sided ideal. Now you can also play the game the moment. Okay, so you can say that. Let me give some more examples. Say maybe it's a polynomial ring. So let me start with a polynomial ring. Say the simple polynomial ring Zx. So this is collection of all the polynomials with coefficients of integer, right? So in suppose this is my R. So here also you can define the ideal. So for example, you remember I defined a map last time that from, okay, so phi is a map from say R to Z. R means this Zx. So yeah, so Zx to Z by phi of fx going to f of 0. Okay, and we also showed that this kernel of phi is, okay, so this is this is, you should check kernel of a homomorphism is always an ideal, is an ideal of Z, right? Now what is this kernel, how this look like? Okay, so this is a simple question, how this look like. Okay, so So let me find out this. So what does that mean? So kernel of phi is all those fx fx belongs to zx such that f of 0, so see, this is image is f of 0, right? So that has to be 0. So f of 0 equal to 0, right? So what does that mean? That means f of 0 equal to 0 means there is no constant term, right? So what does that mean? That means the polynomials are multiple of x. So this is nothing but so this is nothing but x time this is x. You take any polynomial and then multiply by x, right? And this kind of ideal we define by this symbol. Ideal generated by, we say that this is an ideal generated by x. Okay. Similarly, when we define r of I, so that also you can write down by this symbol or I or whatever. So they are called ideal generated by that element. Clear? So here the kernel is an ideal which is generated by a single element x. Okay. So there are plenty of such examples that you can easily find out for fine-tuning also. So you find out, for example, you can do homework. Third example, suppose this z mod say 10z. Okay. Now find out. So find out all the ideals in this in z mod 10z. Okay. Find out how many ideals are there. Set this D. So these are small problem you can ask and you can do it. Okay. So maybe I will stop today's lecture. So today we have learned a very important idea. It's called an ideal of a ring. Okay, and obviously we started with subrings and then we said that we check under which property the subring the quotient the quotients become a ring, and it's called the quotient ring, and we find out that it is actually nothing but the property is similar to the property of normal subgroup, right? It is kind of absorbing, and this property is called is an ideal. Okay, so I will stop here.